Welcome to lecture number 18 of the course on high performance computing. Just to remind you what happened in the previous lecture, we were trying to understand what happens when a program of ours runs on a computer system. We saw that the operating system is sharing the resources of the computer system among all the programs in execution. In particular, as far as the use of the one processor on the system is concerned, you'll remember that we looked at how the operating system, by actually viewing each process as a data structure, as a collection of data and some operations associated with it, can shift attention from one process to another process. And this was well illustrated by a very simple diagram that we came up with, called the phase operating system's perspective of how the process states transit, or the process state transition diagram. So I'll just start off by reminding you about that. So in the process state transition diagram, there is one state associated with each possible condition that a process could be in. At any given point in time, one process can be running on the CPU. Several processes could be waiting for events of various kinds to happen. Once the events happen, each of those processes could become ready to be allowed by the operating system to run on the CPU. So now the interesting question became, when we have one program running on a system sharing the resources with 100 other processes, what do we need to know about what happens to our process? And we see now that it may be useful to know something about how the operating system decides when a ready process should be allowed to run. And that's what we're looking at. We're looking at various possible strategies the operating system could use. The event of switching from one process to another we described as a context switch. It involves a little bit of overhead because the hardware state of the process which used to be running must be remembered, because it will subsequently have to run at some point later in time. And the hardware state of the process which is to start running on the processor must be put into the processor itself, the registers of the processor. So this is what we call the context switch. And the operating system's process scheduler could be written to use many different kinds of policies, depending on what the perspective of the person who designs the operating system is. And we saw that the two possible higher level considerations could be either to try to come up with a policy that reduces the average amount of time to execute a program across many programs, alternatively to try to be fair to all processes. And various possible process scheduling policies could be designed. We saw that if one takes the viewpoint that the operating system should not preempt a process, in other words, allow a running process to run as long as it wants, then there are one or two possible policies, such as first come first served, which would be implemented using a queue of processes, but which would suffer from something like an infinite loop running in a process, because that process would actually never yield the CPU. The alternative is to use non-preemptive policies such as shortest process next, which once again will not do anything about the infinite loop process, but will be a little bit fairer among processes in order to reduce the average program execution time. Since neither of these policies is ultimately fair enough for the requirements of a real operating system like Linux or Unix, we learned that in practice preemptive policies are what we should expect. A preemptive policy is one which periodically will switch from the running process to one of the ready processes in order to be fair to all processes. And one simple idea in this direction was the round-robin policy, which we described in this way. It maintains a first come first served ready queue. A newly arriving process, a newly created process, will be added to the end of the ready queue. A process which is running at some point in time will be preempted at the end of its CPU time slice in favor of the process which is at the head of the ready queue. The process which was preempted itself will enter the ready queue at the end. So in this way, processes periodically get some amount of CPU time and then go to the end of the ready queue and so on until they finish their execution. So in that sense, I described it as much fairer than any of the non-preemptive scheduling policies. We also saw that this scheduling policy would not suffer from an infinite loop in a program, because at the end of the CPU time slice, even if the process was running an infinite loop, it would be preempted from the CPU in favor of one of the ready processes. Okay, now we're going to look at alternatives to the round-robin scheduling, which would try to take other considerations into account. in order to, in essence, to try to become fairer to processes. In a commercial system like Unix or Linux, we suspect that fairness might be an important consideration. And in this direction, rather than just inserting processes into the first come first serve queue on the basis of their time of creation, some other consideration could be used. So the idea of any priority based scheduling scheme is that the ready queue need not be ordered on a first come first served basis. The first come first served basis is in some sense arbitrary. It does not take into account any attributes of the process other than its time of creation. And in order to be fair to processes, it might actually make sense to have other considerations which could be described by what is called a priority. You have heard the word priority in connection with in common everyday usage. Here the word priority would imply that all processes are not considered to be equal at all points in time. Some may have higher priority or higher privileges or higher preferences than the others, and the scheduling policy could take a priority into account instead of treating all processes as exactly equal. Okay, now if one uses a priority based scheme, the ready queue, rather than being first come first served, could be ordered on priority. What do I mean by ordered on priority? Now, whenever we think of a ready queue, we think of a data structure in which there is a back and a front. The idea is that any newly arriving process would typically enter at the back, and when a process has to be scheduled, in other words, one of the ready processes in this ready queue has to be made into the running process, one would take the process from the front of the ready queue. Now, if I am ordering the ready queue on priority, what this means is that processes will not enter the queue based on the time of creation or anything like that. Rather, they will enter the ready queue at the appropriate point depending on their priority. For example, let's suppose that there is a process in the ready queue with priority 5. I'm describing the priority of a process by an unsigned integer. We'll assume that the higher the number, the higher the priority. The next process might have a priority of 3. The next process might have a priority of 2. Now, let's suppose that at this point in time, a new process comes into existence. You'll notice that I have ordered the priority queue in terms of priority, the ready queue in terms of priority. The process with highest priority is at the front of the queue, process with second highest priority is next, and so on. Suppose that at this point in time, a process with priority 4 comes into existence due to a fork or something. Now, in the default FCFS, first come first served ready queue, the process with priority 4 would have entered at the back of the queue and would have appeared in the queue after the process with priority 2. But if I order the ready queue in terms of priority, then the process with priority 4 will enter the ready queue here, and the other processes which had priority 3 and 2 would move back in the ready queue. So in this way, we are giving slightly better treatment to the process which has priority 4 because of its priority rating. Right? So what could the priority be decided based on? Now, many examples which one could think of, but one possible idea is the one which I've written over here. The process that has not run for the most time could get the highest priority. Now, as the priority of processes are different, there is this possibility that a process with very low priority may in fact not get the chance to run in the CPU for a long duration of time. And this could be used to actually enhance its priority. Right? So that's the idea which is expressed in this example. A process that has not run for a very long amount of time could be given a higher priority. So let's suppose that we have the example shown in the diagram. It could well happen that the process with priority 2 does not get to execute for a long time, maybe because after the process with priority 5 runs and the process with priority 4 runs and the process with priority 3 runs, it's conceivable that new processes with priorities higher than 2 might get created, and they would all enter the ready queue in front of the process with priority 2. So after this has happened for a significant amount of time, it's possible for the operating system to be designed with this kind of a consideration. The process with priority 2, having been deprived of the CPU for a huge amount of time, could be given an enhanced priority, maybe a priority of 6, which would cause it to come to the head of the ready queue. So this is a simple idea. It could be used by the operating system process scheduler to enhance the fairness as far as processes are concerned. Right? So by not treating all processes identically, processes which have been deprived could be given preferential treatment periodically. So this is the idea of any priority-based scheme. And as it happens, the scheduler could do even more. For example, we talked about the idea that associated with the operating system scheduler, there could be a duration of time called the CPU time slice. I gave you the example that 1 second or 100 milliseconds might be an appropriate CPU time slice, and this may be decided based on properties of the processor, properties of the amount of time it takes to do a context switch, and so on. So this is what we might think of as the CPU time slice. And this is the maximum amount of time that a process would get to run on the CPU before it is preempted. But if there is a process which has not run on the CPU for a long time, such as our process 2 in the example, which may ultimately get to run as a process with priority 6, then when it does get to run on the CPU, the scheduler could even give it an enhanced time slice. So for example, if all the other processes when scheduled were getting 100 milliseconds, then this particular process, which had not got the CPU for a long time, might be given 1 second CPU time slice. And so there are other dimensions. Not only is there the dimension of importance of a process as quantified by priority, this could also be used not only in the ordering of processes in the ready queue, but also in the amount of CPU time that they would get when they are scheduled, for example. So this actually opens up a whole possible design space of process scheduling policies, and designers of operating systems could use their discretion in deciding what setting of the different parameters of this design space would be most appropriate to come up with a good, fair, efficient scheduling policy. I'm going to talk about one class of scheduling policies a little bit, which falls in the category of priority-based. And generally one hears them referred to as multi-level feedback policies, a family of policies. And policies of this kind were used in some kinds of variants of Unix. So the ideas along these lines might be what you would see in a Unix or Linux system. Now, just to describe briefly the attributes of a multi-level feedback policy, in general these policies are preemptive and they use priorities. Now, let me try to explain such a policy by looking at each of these two terms, the term multi-level and the term feedback. Now, when you hear the term multi-level, you realize that there are many levels, and the suspicion is that there are many levels of queues. In other words, that the operating system is actually maintaining one ready queue per priority level. So for example, in the previous slide, I had talked about priorities in terms of numbers. I had used the numbers 6, 5, 4, 3, 2 to talk about the different possible priorities. A process with priority 6 was a very high priority or important process from the perspective of the scheduler. A process with priority 2 was a low priority process. Now, the idea of a multi-level scheduling policy would be that rather than maintaining just one ready queue, there would actually be one ready queue per priority level. So one ready queue for priority level 6, one for priority 5, one for priority 4, one for priority 3, etc. And there could be a number of processes in each of these queues. So if there are 2 processes with priority 2, they would be in the last or the lowest in this diagram, priority queue, ready queue. If there are 3 processes with priority 6, they would be in the topmost ready queue. So in essence, the operating system might choose to keep separate ready queues for each of the priority levels, and then there's no question of reordering the elements in the queue, because if you look at the queue for priority level 6, all the processes have priority level 6, and therefore the question arises, in what order should they be included in the queue? And then the answer which one could see clearly is that the queues could then be maintained as first come first served queues. All the processes in a particular queue have equal priority, and therefore the queues by definition could be first come first served queues, which is what we normally understand by the term queue anyway from a data structures course. Right? So now the question becomes the following: if there are many ready queues, when the time comes to identify a process to schedule, in other words to make as the one running process, from among all the processes and all the queues, which one should the operating system process scheduler pick? Now obviously if there are any processes in the highest level priority queue, the process from the front of, for example, if there are processes in the priority queue, the ready queue for priority level 6, then the process from the head or front of that queue could be scheduled. But what if the ready queue for priority level 6 is empty? Then it makes sense to have the policy designed so that it then looks into the priority level 5 ready queue. And if that too is empty, it could look into the priority level 4 ready queue, and so on. In short, one could describe the scheduling policy as schedule the process which is at the front of the highest priority non-empty queue. So start looking at the highest priority queue. If it's not empty, take the process from the front of that queue. If it is empty, go down to the next priority queue, and so on. So this gives a well-defined mechanism for deciding which process to schedule next. Now, the danger of this kind of a scheduling policy with only multiple levels is that it is no different from what we had seen before, unless there is some mechanism by which the priority of a process can change. So if a process of priority level 2 can become a process of priority level 6, then this can be used by the operating system scheduler to create a level of fairness to processes. So that's where the term feedback comes into the picture. When you hear the term feedback, you imagine some kind of a system in which some attribute of the system is used to change the properties of the system, either through enhancing or reducing some attribute of the system, negative or positive feedback. So the idea here in terms of scheduling might be that based on what has happened to a process up to now, one could decide whether to enhance or to reduce the priority of the process, or possibly to keep the priority of the process the same as it is right now. So that's what the term feedback is going to imply. In this class of scheduling policies which I've described as multi-level feedback, the word feedback is going to mean that the priorities are not fixed. The priority of a process is not fixed. During the lifetime of a process, its priority could increase or its priority could decrease, depending on how the operating system process scheduler is designed to deal with fairness. And we've seen an example where it might make sense to increase the priority of a process. Suppose, for example, that a particular process has been at priority level 2 for a long time and has not got CPU time, then that could be used as mechanism that could be used as an indication that the priority of that process should be increased. On the other hand, if there is a process which has received a lot of CPU time because it has been at level 6, then the fact that it is at priority level 6 and has received a lot of CPU time could be used to reduce its priority level, maybe bring it down to priority level 5. Right? So this combination of having multiple levels, in other words priorities, and feedback, in other words the priority is not being fixed, but the priority of a process potentially increasing or reducing, could end up with policies that are not only dynamic in terms of how they treat processes, but also as fair and as efficient as could be designed. So these are quite flexible process scheduling policies compared to the simple alternative of something like Roundrobin, which would have put all the processes into a single first come first served ready queue, and after scheduling a process, just bring it to the back of the ready queue. So the multi-level feedback provides a lot more flexibility to the designer of the operating system. Okay, now given this rough introduction to how the operating system might be doing the scheduling of processes, we get the idea that the lifetime of when we submit a program for execution, we can think about its lifetime. I have used this term before. Let me just formally say that what I mean by the lifetime of a process is the time between its creation, which happens due to a fork system call, and its termination, let's say, which happens typically due to execution of the exit system call. Right? So this is the standard use of the term lifetime that we have been throughout the course. I talked about the lifetime of a piece of data, the time interval between its deletion and its creation. We now talk about the lifetime of a process. Now if we think about the lifetime of a process and we want to quantify it in terms of time, we need to look at timelines. And we have this clear picture in our minds that from the process state transition diagram, where we have at least 3 states, running, ready, and waiting, we have this clear idea that process P1 could be running right now, then it might be in a waiting state because it does an I/O operation. When the I/O operation completes, for example, it could end up in the ready state, and then from there it could go back into the running state, and then after being in the running state for some time it might get preempted, for which reason it goes to the ready state, and so on. So a process during its lifetime is going to spend some time in the running state, some time in the ready state, some time in the waiting state. And therefore we need to look at timeline to get a better idea of what lifetime might mean. So let me just draw a timeline. As usual, I draw a timeline as a line which starts at some point in time and goes on indefinitely into the future. Now let's consider what would be the various kinds of things we would see on the timeline if there were many processes contending for the CPU. In other words, let's suppose I have 5 or 6 programs running on a computer system. This might result in 5 or 6 processes. All of these 5 or 6 processes at some point or the other will hopefully end up being running. They could end up being waiting, they could end up being ready. And what I'm going to draw on this timeline is a history of the order in which the different processes actually get to run. Since it is only when a process is running that it is making use of the CPU, and that its instructions are getting executed, and that its data values are getting modified, and so on. So on this timeline, we're basically going to show intervals of time when a particular process is running. That is the important state from our perspective. So it might happen that the first process which gets to run is process P1. So I show that by indicating an interval on the timeline and labeling that interval as P1. The suggestion is process P1 is running in that interval. At this point in time, something happens. Possibly process P1 gets preempted if this is a preemptive scheduling policy, which is why there is an end of the interval, and conceivably process P2, some other process which was in the ready queue, ends up being the running process. And just remember that we have this clear notion that in order to switch from process P1 to process P2, there is a little bit of overhead. There's this thing called the context switch. So the event that happened over here was the context switch from process P1 to process P2. And you'll note that if the CPU time slice was 1 second, then it's conceivable that the duration the process P1 was executing was 1 second, and it's conceivable that the duration for which process P2 will execute is 1 second, and that the context switch itself is not instantaneous, but is likely to take a small percentage of 1 second. For example, I had used the example last time of a few microseconds. So it is something which takes time, but it's such a small amount of time compared to the other events of interest, the intervals on the timeline, that I'll just show it by that very thin line. But do remember that the context switch does take some small amount of time. The amount of time it takes is related to the amount of time that it takes to remember in memory the state of process P1 and to put into the hardware registers the beginning state of process P2 as it should have been based on where it stopped execution the last time it was running. Okay. So the history as we have it now, process P1 was the first process to be scheduled. This was followed by process P2, and after process P2 was either preempted or did a long duration operation like a file I/O or a page fault or something like that, it's possible that process P3 executed, and so on. So there's going to be a history of the various processes as time went on. You notice that after P3 I show process P1 executing once again. So P1, which had got its first chance to run on the CPU over here, gets a second chance to run on the CPU over here. Now what are we showing on this timeline? We're showing the events of interest as far as the operating system is concerned. And in fact we're showing what you might describe as the real timeline. Right? I continue to show process P3. The implication from this diagram might be either that process P2 had finished execution, the program had terminated, or it could be that after process P1 had executed, the priority of process P2 became less than the priority of process P3, which is why process P3 followed process P1 the second time around. So that's a vagary of the process scheduling policy. We won't worry too much about that. The important thing to notice is that on this timeline we are putting down information about what happened as far as the use of the CPU is concerned. This is the history of processes running on the CPU. It does not contain information about the history of processes waiting or the history of processes spending in the ready queue and so on. Those could be separate kinds of timelines if that information was important to us. Now we do need a term to refer to this kind of time, because we're actually going to talk about other versions of time. And since the timeline that we've drawn over here is showing the sequence of events that happened as far as the CPU is concerned, in reality, we could refer to this as real time. This is not some kind of a fictitious time or imaginary time, such as when we talked about memory, each process had its imaginary or virtual perspective on what addresses were. Here, the events that are happening are what actually happened on the CPU. Process P1 did run on the CPU first, then there was a small duration of time when the context switch occurred, then process P2 did run on the CPU, and so on. So in that sense, one could refer to this time, the time that we've been drawing in this timeline, as the real time. What do I mean by real time? What I mean by real time is what you may also call wall clock time. The term wall clock time is used just to disambiguate from any other possible kind of real time that you might have in mind. The picture that you should have in mind when you think of the wall clock is that on the wall behind you there is a clock, and you know that that clock ticks. Right? Every second the second hand moves forward by 1. If it's a digital clock, it might be a little bit different, but you know the rate at which time moves in that for that clock. So we're essentially saying that time moves along this timeline at the same rate that time moves along the wall clock. In other words, we're talking about the same physical time that we deal with in our daily lives, the time as I see advancing as along my watch. So in general we think of these two terms, real time and wall clock time, as being synonymous. In some books you may hear people talking about real time, in other books you may see people talking about wall clock time. In fact, another term which is sometimes used to describe this concept of time is to refer to it as elapsed time, or the amount of time that has elapsed since the beginning of the timeline. In this case, it might be when the system was booted up, when I turned on the system. That might be the 0 that I see over here. And so these three terms, real time, wall clock time, and elapsed time, are to be viewed as being synonymous. And in general, you may find, in fact, in general you will find all three of these terms used depending on the preference of the person who is describing the time. And whenever you hear any of these terms, think about your watch or the clock on the wall, a correctly running clock on the wall. Now, the question which has been in your mind ever since I put up this slide, when I titled the slide about time, would have been, obviously, what other kind of time could there be? Now, thing to note is that when we talked about main memory and we talked about the CPU, at the beginning it was fairly clear to us that whenever we talked about a memory address, we were talking about a main memory address, until we introduced the notion of protecting one process from another, and the notion of having virtual address spaces, or virtual addresses, where we actually had separate addresses for each process. Since the process is the important entity as far as the execution of programs is concerned, the process is the unit of resource management by the CPU, it stands to reason that we might have another perspective of time, and if on a computer system, and if there is another perspective of a time, it could be a per process notion of time. In other words, I could have another timeline specific, let's say, to process P1. And if I was to label this timeline, I could not just label it time, since that would be, the word time is now ambiguous. It could mean the kinds of time that we had in the upper timeline, or it could mean the kind of time that we have on the lower timeline. Therefore, in future, whenever I talk about time, I will have to qualify it by explaining whether I mean real wall clock or elapsed time, or whether I mean virtual time. And if I'm talking about virtual time, I'll have to qualify it by which process I'm referring to in that timeline. Now, in this particular timeline, very clearly, I'm drawing a timeline which is the virtual time of process P1. And what we mean by the virtual time of process P1 is going to be related to its intervals of time when it is running. So once again, our emphasis is on running, as the timelines are going to show us running times, since the waiting and times that a process is in the waiting state or in the ready state are not under the direct control of the programmer, whereas the times which are on this line are under the direct control of the programmer and therefore of interest to the programmer. Right? So here we are trying to get a timeline in which all that is shown are events relating to process 1 and events relating to process 1 being running. And if I had to fill up this timeline, it would show, if I'm drawing the timeline up to this point in real time, then the process 1 virtual timeline would end over here, because we know that process 1 was running on the CPU for 1 second, and then later on it ran on the CPU for maybe half a second. That looks like a smaller interval. So it ran on the CPU for a total of 1.5 seconds in this real time interval. So in the real time interval, which might be about 7 or 8 seconds, process P1 ran for 1.5 seconds. So this real time interval, let's say it's 1, 2, 3, 4, 4.5 seconds. So in this real time interval of 4.5 seconds, process P1 ran for an interval of 1.5 seconds. And what I'm showing in this diagram is the process 1's perspective of time. Because you'll note that the other intervals of time do not really exist for process 1, in the sense that it was not active on the CPU when process P2 was running. It was not active on the CPU when process P3 was running. And therefore, this is a complete picture of time as far as process P1 is concerned, in terms of its progressing from one state, in terms of its variables changing or its instructions being executed. Now, we can add one more complication into such a diagram, given our exposure to process lifetime, you'll remember that when we talked about system calls, I introduced the idea that at any given point in time, a process could be running, but further it could be running either in user mode or in system mode. And up to now we understood that a process would be running in system mode when it makes a system call. And if it is just running in its ordinary mode where it's executing the instructions of its own program, not the very special instructions within the system call, which is part of the operating system, then it is actually just running in user mode. And we had this idea that the operating system actually makes it possible for us to find out how much time our process was running in user mode and how much time our process was running in system mode. And over here we actually had used the term CPU time, but we now understand that what we're talking about here is this concept of virtual time, the time specific to this process. Right? So I could not use the term virtual time earlier, which is why we were talking about CPU time. But now we know that the CPU time is shared among many processes, and that in order to disambiguate what we mean by CPU time, we could more profitably use the term virtual time. All right, so we could go back to the diagram we had just seen, where we had both the full picture of the CPU from the perspective of how its time is being used among all the processes, to the picture of time in terms of one specific process, and realize that saying that process P1 got 1.5 seconds of CPU time could be further refined to saying that if I looked at the virtual timeline of process P1, there would be some intervals of time when it's running in user mode and some intervals of time when it's running in system mode. So I could actually color code in this particular diagram. I'm going to show in brown the intervals of time when the process P1 is running in user mode, and in yellow the intervals of time when it's running in system mode. And we would then expect to see a breakup of what's happening in those two time intervals, maybe along the lines of what you see over here. So you'll notice that process P1 starts by running in user mode, then possibly it makes a system call, so it's running in the yellow system mode for some time, then it comes back to the user mode, then once again it goes into the system mode, possibly because of another system call, then it ends up running in user mode. At that point, apparently it gets context switched out, so there's a small interval of time for the context switch, a few microseconds. When it starts executing again, it's executing in user mode, etc. So when I told you that the operating system actually keeps track of how much time your process is running in user mode and how much time it's running in CPU in system mode, the implication was that this bookkeeping of what is the sum total of the intervals of time which are brown as far as process P1 is concerned, and what is the sum total of all the intervals of time which are yellow as far as process P1 is concerned, is done by the operating system, and it's something which you can get access to. So there are mechanisms, system calls, through which you could request the operating system for this information. And as we saw, this might be useful for you in improving your program, in using mechanisms that we will talk about later. So the notion of the process virtual timeline, in other words, trying to restrict one's attention to what is happening to your process rather than the other processes which happen to be running on the system and have nothing to do with you. So in other words, concentrating on process virtual time rather than on what's really happening in terms of the movement of time as the world knows it, may be of relevance to us in improving the qualities of our programs, understanding how our program is doing things, and further the breakup between doing things in user mode and in system mode. Okay, now before we move forward, I'll fill in a few gaps which remain from our discussion of how the operating system manages CPU time. And one interesting question which would arise if one thinks about it deeply is the one on the screen. How is a running process preempted? Now you'll recall that I mentioned that if one is using a preemptive process scheduling policy, the idea is that the operating system process scheduler will not allow a process to run indefinitely, but periodically, let's say after it finishes its CPU time slice, it will preempt it. Now if you bear in mind that preempt it and switch to one of the ready processes in preference, rather than continuing the execution of the process in question. Okay, now if you think about this a little bit, there is a problem because the operating system itself is a piece of software, and in order to preempt a process, the operating system preemption code, in other words the instructions within the operating system which do preemption, which I'll refer to as preemption code, must run on the CPU. What does the operating system preemption code do? Basically, the operating system preemption code will include instructions which do the scheduling policy, right, which look into the ready queues, etc. It will include instructions which will do the saving of the hardware context of the running process. It will include instructions which do the restoring of the hardware context of the process which is going to be scheduled. So a fairly large number of instructions, all of which I am describing as the operating system preemption code. But in order to achieve the preemption, in other words, for this to happen, the operating system must be running. The instructions of the operating system must be running. But unfortunately, process P1 is running, and process P1 will continue to run until it is preempted. Hence the problem. How can the operating system run its preemption code before process P1 has been preempted? See, until process P1 is preempted, process P1 occupies the CPU. So this is the nature of the problem. So very clearly, this is not going to require some kind of hardware support. This is not something that the operating system can manage as a software entity. And this is just a rewording of the question. How does the operating system get control of the CPU from a running process, P1, for example? P1 was the running process in our example, in order to run its preemption code. And as I had indicated, this may actually require hardware support. And the form that the hardware support takes is a small piece of hardware called the hardware timer. And essentially, when you hear the word timer, you normally think of something which counts time, and that's basically what this piece of hardware is doing. It is basically some kind of something like a clock, which periodically will try to grab control of the CPU. And the way that it grabs control of the CPU is using a mechanism called an interrupt. Now, what is the hardware timer? What does the hardware timer do? It basically periodically generates an event. The period of this event could be a few milliseconds or whatever. So what I mean by period is the frequency with which the event occurs. So if the hardware timer is such that it generates this hardware event once every, let's say, millisecond, then the period would be 1 millisecond. So it's a hardware generated event. So there's a piece of hardware which is doing this, part of the CPU. Now the mechanism that's going to have to be provided within the CPU is, whenever this kind of an event occurs, the hardware must automatically transfer control to the operating system. So the hardware has to be built, the processor has to be built, so that whenever an event of the kind mentioned in the first bullet occurs, automatically, without the need for intervention from any form of software, control gets transferred to the operating system code, specific operating system code which is called the timer interrupt handler. So this gives the operating system a mechanism through which it can grab control of the CPU, because we now have a guarantee that if the period of the hardware timer is 1 millisecond, we have a guarantee that once every 10 milliseconds, the operating system's timer interrupt handler, in other words, a small piece of code, part of the operating system, will get executed. Again, so going back to our timeline, we do the timeline like this, but we now need to understand that once every millisecond, which is very frequently in this timeline, remember this interval is 1 second. Therefore, 1,000 times, if the timer interrupt interval is 1 millisecond, then 1,000 times in this interval, the operating system is actually getting control. So we realize that with this mechanism, the operating system gets control whenever it wants to, as far as the control of the CPU is concerned. Okay, so very clearly, in those 1,000 times that the operating system timer interrupt handler gets controlled, 999 times it won't execute the preemption code, and the last time it will execute the preemption code, as a result of which process P1 gets replaced by process P2 through the context switch. Okay, now this the concept that we have over here, where there are events which are automatically, in which the hardware automatically causes control to be transferred to a piece of operating system code, will require that the hardware be designed to do this. So it must have a very well defined interface for operating systems and the hardware to interact with each other in this way. So a very well defined sequence of events that must happen for this kind of a commitment to be made by the designer of the hardware. Okay, so very clearly we're talking about a slightly more general phenomenon than just to solve the problem which is listed on the screen. And in fact, the interrupt which I talked about over here, the hardware timer interrupt, is merely an example of a more general phenomenon which is known as an exception. So I'd like to spend a few minutes talking about exceptions before we move forward. So what we need to understand here is that there is something called an exception, and today's processors are designed so that whenever an exception occurs, and there could be many different kinds of exceptions, but whenever an exception occurs, control is automatically transferred from whatever happened to be running on the CPU before. Control automatically gets transferred to a special piece of operating system code, and depending on what the exception is, a different piece of operating system code might be the beneficiary. For example, if the exception that just occurred was a timer interrupt of the kind that we're talking about over here, then control automatically gets transferred to a piece of operating system code called the timer interrupt handler, which would contain the appropriate activity as far as handling or dealing with the timer interrupt is concerned. So apparently there could be other kinds of exceptions, and therefore we will need to learn a little bit more about this. So let me, on a brief aside, talk about exceptions. So by the very word, by its very name, we understand that exceptions are some kind of rare or unusual. So the word exception here means rare, unusual, not in the common sequence of events, or exceptional events. So these are exceptional events that occur during program execution and are automatically handled by the processor hardware, in that depending on what the event is, a specific piece of operating system code would be transferred control to automatically. Now in general, one could talk about two different classes of events. I'll use the word classes rather than kinds of events. And these two classes, there are two different classes of exceptions, and these two classes of exceptions are referred to as traps and interrupts. We had seen the word interrupt before. I talked about the hardware timer interrupt. In other words, an interrupt or an exception generated by the hardware timer. So in general, when we talk about exceptions, we need to remember that there are two kinds, in traps and interrupts. Now a trap and an interrupt are different in that the trap is a software generated event and an interrupt is a hardware generated event. So we saw that the hardware timer is a piece of hardware which periodically, possibly once every millisecond, generates an event. In that case we called it an interrupt. Now the suggestion from this classification is that there are also some kinds of exceptions which are generated not by hardware pieces, not by specially designed pieces of hardware, but by software. And the question you'll be wondering, what is I won't actually emphasize what the terms synchronous and asynchronous mean here. It's not important. It's not important for us in our current context. So the question of what kind of exceptional situations might be generated by pieces of software. And in fact, we've already seen at least one, and that is the page fault. If you think about it, a page fault occurs because, let's say, a load word instruction is executed, and the effect of the load word instruction might be that an address is generated, and it may be found out that that address is not an address which currently has a page table entry in the MMU, in the TLB, or it may not be an address which has a valid page table entry, in that the page table entry associated with that virtual address might not have the valid bit set. In some sense, one could say that this is a software generated exception. I view it as an exception because we know that automatically when this page fault occurs, control got transferred to the operating system page fault handler. That's a common term. You'll recall that we talk about an exception being handled, and the piece of operating system code which handles the exception is what we refer to as a handler. So we had previously seen what happened as far as the page fault handler is concerned, and we can now think of the page fault as being this kind of an exceptional event. It's relatively rare. It hopefully does not happen on every memory reference, but when it does happen, the processor has to be diverted from what it is currently doing to actually executing the operating system's piece of code called the page fault handler. We've also seen that the system call is something which would be caused by the execution of an instruction. In other words, the syscall instruction in the MIPS instruction set. The syscall instruction is an ordinary user mode instruction. It's not a privileged instruction. But when this instruction is executed, control automatically gets transferred to the operating system region of code which executes that particular system call, right? And through a system call handler of some kind, conceivably. So once again, it was a situation where control automatically got transferred to a piece of the operating system code, and we have seen both of those before. Let me just mention that it's also possible that there are other events of this kind, such as if there's a program which executes a divide instruction which results in a divide by 0, things could be set up so that this is handled by a divide by 0 trap handler. So different kinds of traps for different kinds of exceptional situations that could be caused by the execution of instructions. Interrupts, on the other hand, are exceptional situations which are explicitly generated by the hardware. And we've seen one example of an interrupt, that was the hardware timer interrupt. And we saw that this was very important from the perspective of the design of the operating system, since it is only through having a periodic timer interrupt that the operating system could periodically get control of the CPU in order to do its management of the resources. Otherwise, the operating system would lose control of the CPU to an infinite loop process and never be able to recover it. Okay, now we could also think about other pieces of hardware in the system and ask the question, for example, when I hit a key, how does that mechanical device on the keyboard cause any information to enter into the computer, which is, as far as we know, made out of circuitry? And we can now look at this from the perspective of the following sequence of events. When you hit a key, mechanically, something is happening inside the keyboard. The keyboard itself contains circuitry, and the pressure on the key is going to cause some of that circuitry to generate a keyboard event or a keyboard interrupt. And essentially what is going to happen when you press the key is that the keyboard interrupt gets generated, control gets transferred to an operating system, a small piece of operating system code called the keyboard interrupt handler. And what the keyboard interrupt handler does is to transfer the character which you had typed in. So if you had pressed the A key, then within a buffer within the keyboard, the character A is going to be generated, and the character A is going to get transferred by the keyboard interrupt handler into somewhere in memory. So you may have typed the key, and then you may have included in your program some kind of a scanf to read input. So ultimately from the keyboard interrupt, from the keyboard interrupt causes the piece of the character to get transferred, and then ultimately the data will go to the buffer which you have mentioned in your scanf call. So all of this is triggered by an interrupt as far as the keyboard is concerned. Similarly, operations on disks also may have interrupts associated with them. For example, we talked about the fact that when a process let's say does a file read operation, this is going to cause a read operation to start on the disk. Now this is an operation which could take milliseconds, conceivably a large number of milliseconds to complete. So the process itself is going to go into a waiting state. It was in the ready state when it executed the file operation, but the process may go into the waiting state at the discretion of the operating system designer. Subsequently, the disk or I/O operation will complete, and the data will be available somewhere in the disk, ready to be transferred to the processor or memory, from the processor to memory. And in doing this, it's possible that the disk can indicate that the I/O operation has completed, possibly by an interrupt, to grab the attention of the processor to execute a disk I/O interrupt handler routine to do the transfer of the data. So it's conceivable that things could have been set up that way. So associated with different input and output devices, or with different pieces of hardware in the computer system, there might be the generation of interrupts in order for the interaction to happen. And therefore traps are important from the perspective of the events that you generate within your program, and interrupts are very important from the perspective of interaction with the outside world, and in particular the I/O devices. We've now seen the special case of the timer interrupt handler, important for the operating system design. The very fundamental operating system design may require this existence of a timer interrupt handler as we had described it. Okay, now with this idea that the hardware must be designed to handle exceptional events, and that the exceptional events could either be traps or interrupts, I'll sketch out in more detail what happens when an exceptional event actually does occur. So we've seen that when an exceptional event occurs, at the beginning an interrupt or a trap gets generated, and I lay the blame for this at the hardware. Okay, now if you think about the traps that we talked about, if there is a page fault, the question of how is the page fault identified will arise, and you realize that the page fault occurred because of an instruction in your program, and hence we think of it as a trap. but the page fault will actually be recognized by the memory management unit when it tries to translate the address. Similarly, the system call is an instruction in your program, but the fact that this is a system call is identified by the hardware which executes the instruction fetch, instruction decode hardware. So ultimately we could lay the blame for handling the exception initially at the hardware. So I start the description of what happens on an exception with the hardware. Right? If it's a trap, there is some prior history relating to the software which we have already studied adequately. So what should the hardware do when it realizes that an exception has occurred? It could be a trap, it could be an interrupt. Now the first thing that it will have to do is, it will have to bear in mind, the hardware will have to be designed to bear in mind that in the very near future, control is going to have to be transferred to an operating system routine called the handler. It could be a page fault handler, it could be a timer interrupt handler, depending on what this particular exception is. But control will have to be transferred to the handler, which is a special piece of operating system code. This is going to mean that whatever is currently executing on the processor, which could be process P1 executing in user mode, is going to have to be stopped for the moment. And if one is going to stop the execution of process P1 for the moment, then its current state will have to be saved, because later on the state will have to be restored. Therefore, the first thing that the hardware will do when an exception occurs, it cannot just immediately transfer control to the handler. It will have to save the processor state in memory. After it has saved the processor state, since this state will be necessary when one is coming back from the exception, it can transfer control to the corresponding operating system exception handler. As I said, it could be the page fault handler, it could be the timer interrupt handler. And now the control transfers to the software, which is the exception handler. What does the software do? Again, depending on what the exception is, the software would have been written to do certain action. For example, we saw exactly what action the page fault handler would be designed to do. So the page fault handler does that. So I'll just describe this by saying that the appropriate action is taken as per the situation. So since control was transferred to the correct exception handler, the correct instructions will be executed for the handling of that particular exception, whatever it may be. What about after the exception has been handled? So all the code in the exception handler has been successfully executed. What should be done next? Then it is time to transfer control back to the process which was running when the exception occurred. Now one will need an instruction to do this. One cannot just do this using the jump register type of instruction that we use to return from a function call for various reasons. So this would be done with a special instruction which might be called the return from exception instruction. And an instruction set is going to contain, every instruction set is going to contain such an instruction. We have not talked about this instruction before in talking about the MIPS1 instruction set, because this is not the kind of instruction that you or I would use in our ordinary programs. This is an example of a privileged instruction. It's only going to be used at the end of an exception handler. And an exception handler is a piece of operating system code. Therefore, it was not necessary for us to know about it, since we are worried about ordinary user programs. We are never going to, none of us at the moment, as far as we know, is going to have to worry about writing an operating system. So the exception handler ends with execution of a special instruction which will cause control to be transferred back to wherever it should. So we're now back to hardware, the execution of the RFE, or return from exception instruction. What should happen in this instruction, or as an effect of this instruction? The answer is, this instruction should cause the saved processor state to get restored into the processor, and then it should cause control to be transferred back to the appropriate PC value. So that wherever we were over here, in other words, whatever process happened to be executing, it might have been process P1 executing at the PC value hex 1000, that's where control should be transferred back to process P1, and we're back to process P1 because we restored its save state, and resuming from the correct PC value, which we knew because that was part of the saved processor state. So with this we have some idea about what an exception is. We have some idea about how an exception is handled. And just to sum up what we've seen in today's lecture, we saw how operating system process scheduling policies might be made a little bit more flexible than what we had seen in the previous lecture, largely from the perspective of allowing the scheduling to be done as fairly and efficiently as possible. We saw that it's important for the operating system to have some way to grab the CPU from the currently running process. Otherwise, the very idea of preemption would not be possible. I mentioned how this is typically done through a mechanism called an interrupt by having a special piece of hardware called a hardware timer, which periodically generates an exceptional event called an interrupt. Interrupts are important events in a computer system. They are examples of more general events called exceptions. There are two kinds of exceptions: traps, which are software generated, such as page faults or system calls, and interrupts, which are hardware generated, typically by I/O devices or a piece of hardware like a timer. And the hardware must be built, hardware must be designed, if it is going to use operating systems of the kind that we have seen, to handle these kinds of exceptional events by saving the state of the processor, transferring control to an appropriate operating system handler, and then returning control with the restored context of the originally running process. With this, we have a fairly good idea about what's happening behind the scenes when our programs execute from the perspective of operating system process scheduling. And we'll continue with a few more closing comments in this area in the next lecture. Thank you.